everybody. It's an immense pleasure to have the opportunity to welcome you here. So, either the people present in the lecture room or people who are following the conference remotely. And, among these participants, I imagine that some participants will be occasional. Some people are actually probably sleeping at the moment because they're coming from faraway places. And, of course, we are extremely happy to be able to be together in a large group. This is something that has, missed a lot over these times. And I think we are quite lucky, in fact, to have this conference scheduled at this particular moment where things are reopening and maybe before things are closing again. So, okay. So we are very happy that of course, we would have preferred that more speakers could be here, but still we are very happy to be able to hold this event in a hybrid form and to see so many people here. And we've missed this time where we could see each other's face, breathe the same air, and share the same germs. Okay, and in fact, let's hope that this hybrid mode will in fact allow people to gather in even more, in even bigger numbers than would have been possible otherwise to celebrate Jean's birthday. So let me say just a few words about organization. So this meeting has been organized. So would it be possible to switch to the slides? Yes. So this conference has been organized by a scientific committee, and here are the people of the committee, and we thank them very much for their advice. The organizing committee is here. So most people are in this room. Unfortunately, Victor Rivero was very sad that he couldn't come, but it wasn't possible for him to fly from Mexico. And a particular thanks to Frau Franziska Robman, whose dedication has been fantastic and whose help was very precious in organizing, in particular, the website and many other things. And okay, so let's just of course the core of this conference is the scientific event. So here is the schedule. So you can either see it on the website, and you can also have it printed on paper. So here the stars indicate people who will give their talks online. So again, we really did our best to be able to gather people, in particular from the UK, but due to the recent events, it was not possible. We are still very happy that they can participate online, and in fact, we are also very happy that some people could make it from the US and from Mexico and from Switzerland. So I think we can be happy about the outcome. So some quick points about organization. So let me recall that there is a conference dinner on Thursday at 7 p.m. and it is mandatory that you register. We have still some many slots available. So please do register on the link that you received via email before today at 4, let's say 5 p.m. We need to tell the people how many we will be. Okay, and another thing. So we are still talking about food. So during the lunch breaks, we are all on our own, but there are many restaurants around campus to enjoy. Okay. Quick points about security. So we will ask people to apply reasonable, social distancing and wear face masks in the lecture room, except for the speakers. Okay, and one thing that is important is that thefts are unfortunately commonplace on this campus. So when you are leaving the room, please carry your bags with you, especially during the coffee breaks. Okay, the amphitheater will be closed during the lunch breaks, but still, it's important that you shouldn't leave anything inside the lecture room. Okay. Okay, so a quick word about our sponsors. So thanks for the generosity of those many sponsors, and in particular, thanks to the generosity of our main sponsor, which is the University of Zurich via Jean's funds. And let me actually take this opportunity to say just a few words about Jean. Oh, so before that, I just also wanted to say that we thank in particular maybe also Sorbonne Université via the laboratoire LPSM, who actually allowed us to have this amphitheater for this lecture room for the week. That was an important part in the budget. So I'm seeing if forgetting anything. No, I think that's it. But okay, so let me say just a few words about Jean. So why this conference? I think so Jean is very generous, not only with the money of the University of Zurich, but as we all know, he's extremely generous with his ideas and time. And I think I can speak for all the PhD, ex-PhD students and postdocs. He spends just an enormous amount of time with his students, gives them many ideas. And so this week is just a modest way to repay him a little bit, of what is given us by, uniting, people, friends, and around him. I think also something that we should say is that what we appreciate with Jean is not only his generosity, but maybe I will speak for myself, but kind of simplicity and straightforward approach to things, to mathematics in particular. And when I tried to think about what it's evocative of, I was thinking, in fact, of the clear line of the Franco-Belgian cartoons. I was thinking that, if Jean had been a cartoonist, then maybe he would have been a member of this doctrine of the clear line, la ligne claire, in which every stroke is significant. There is not one stroke too much, which does not prevent from doing very nice and complicated things out of very simple strokes. And a personal memory of that is that during my PhD, he would tell me, just remove all those parentheses and those brackets in your sentences. One sentence, one idea. Every stroke is significant. One line, one sentence, one idea. Well, of course, I don't know the graphic talents of Jean, but if you judge from his papers, you see that clearly he's trying to maximize a ratio ID over number of strokes. But I'm not talking about his graphic talents, right? I'm talking about the way he approaches mathematics. And I'll stop talking about that because I think the scientific talks are here to testify that much better than I will be able to do. But I just wanted to mention that Jean, when presented with complicated problems, likes to present elegant and nice solutions that make the complexity of the problem vanish in front of the simplicity of the solution. So, thanks again. Welcome, Jean, and joyeux anniversaire. Non. C'est bon? Does it work? Yes.
Okay, so I'm here in my quality of director of the laboratoire LPSM that Gregory has mentioned. So I'm very happy to welcome all of you and Jean in particular. So this event is, of course, so an occasion to present the career and the achievement of Jean on occasion of his 60th birthday. But actually, there is another anniversary that I wanted to mention here. Actually, it is also 10 years since Jean moved from Paris to Zurich. So since I was asked to say a few words, I was wondering what I could say. So this seems to me an important point to make. So today the conference takes place here, so which shows that the roots are important and that this is an ideal place to celebrate Jean's birthday. Actually, it was really, I think, beginning of July of 2011 when Jean announced his colleagues, so I was among them, that he would move to Zurich. So it was quite a blow at the time because, well, Jean was probably the most prominent member of our lab at the time. So we were sad. I was also personally sad about that in a rather incoherent way, actually, because I had myself moved a few years before from my home country. But you know, so we are human beings, we are social animals, and separations are usually tricky events. They are difficult, in particular for those who remain, but they can be difficult also for those who leave. So I remember that I said, Jean, that I was, yeah, I don't know exactly what words I used, but anyway, I was sad about his departure. Then I felt guilty, and I offered him a present, a book in German that I had read while I was during a postdoc in Germany. And yeah, actually, you know, human beings also have another quality, is that life goes on. So we get used to everything. We adapt to the new situation. So we could hire someone who replaced Jean later. The first years we kept seeing him because he came giving a course in the master of the lab. And so this allowed him to pick some PhD students and bring them to Zurich. And then also this stopped, but okay, we kept meeting at conferences, etc. So there is a link which has a bond which remains. And again, so 10 years later, I'm very happy that we can again receive Jean and his community, okay, and host this event. What can I say? So, in fact, at that time in 2011, of course, Jean was not the first French mathematician to leave France, but still, it was a period when life in France for mathematicians was rather good. There were plenty of positions at the time. So for young people to become assistant professor, for assistant professors to become professors. So today that's becoming much more difficult. And we see a number of departures from France, which is somewhat new, I think, for the French community. So this is something which deserves some reflection. Actually, I come from a nation which has become a big exporter of mathematicians already long ago. And now it's become a sort of mass movement. So just to tell you, 2 years ago, there was a conference in Italy of the community of Italian probabilists and statisticians. There were 200 participants, and 1/3 were Italians based abroad. Okay, there are actually also Italians which go back to Italy. So this was not common 10 years ago, but now this is happening. But at the same time, it's a community which is which has become quite international. Let's say there must be quite a few also in Zurich. Now for France, that's not the case yet, I think, because well, I don't know. Maybe the French are more. Okay, I don't want to comment on that, but it may happen. Okay, so in the next years, if the situation with the positions remain as it is, since we have very few postdocs, so I have 3 recent PhD students already in Berlin. I don't know. This risk continuing. At the same time, as we say, it's difficult, as I said. So the separations are not easy, but you can adapt to the situation, and maybe also the French community will have to adapt to the idea that spending some time abroad is necessary and even useful. Okay, it's not so bad. So I'm in a good position to tell you that you can live well also abroad. In both senses, okay? And yeah, in a sense, Jean is an example of that. So he has continued his brilliant career in Zurich, but he still has many links with France and actually with the whole planet as the international list of speakers shows. Okay, so I can finish by wishing so Jean in particular, so very brilliant continuation of his career as it has been up to now. So again, I was saddened of his departure, but I am very happy that he's back today, and that this again shows how the bond is strong, etc. Am I forgetting anything that I wanted to say? I don't know. Anyway, we will have the occasion to discuss all this during this week. I hope you enjoy. So the campus is rather pleasant by this season. So welcome to everybody, and enjoy.
Thank you very much, Lorenzo. We are going to start in 5 minutes. So let me recall you that this conference takes place in hybrid format, meaning that not only participants can attend the talks from remote places, but also speakers will give talks virtually. And this morning, we only have on-site talks. We'll be starting with Maria Emilia Caballero, all the way from Mexico City, who is giving the first talk, because I think she's one of the earliest friends of Jean in the community, in the probability community. Am I right? Yeah, he's nodding. He says yes. So let's welcome Maria Emilia, and start at 10:30 for people who are attending remotely. I'm taking advantage of the 4 minutes remaining to communicate to the remote participants that they can ask questions in the chat of the Zoom meeting. Julien Berestiki is taking care of the chair, of the virtual chair, and if something is going wrong, you can warn him by this channel, and also ask questions at the end of the talk. I think we have planned something like 10 to 15 minutes of questions for each talk.
Good morning to everybody. Thank you very much for the invitation. We must wait some minutes until it's 10:30. I would very much like to thank the organizers and the scientific committee for this very nice invitation. And I am very happy I could come at the last minute, really, because that was when the rules of access to France were published about on the 10th of June. And it was a very nice for me to be able to come because I had all the things, sanitary things I had to do to come here. So I would like to speak a little bit about the role that Jan has taken in the development of mathematics in Mexico, in the probability community, of course. And this has been very important for us. So I put one of the posters of the schools, but there are many others. So I described a little bit when Jan came to Mexico. He was coming as a scientific cooperation, and he was supposed to teach. He was teaching at high school or Liceo Franco-Mexicano, but at the same time, he came to the university to participate in our very small seminar that we had at that time at the university. And at the same time, he was finishing his PhD work with Mark Yor, and they were communicating. They didn't have internet. We didn't have internet, so they communicated by written letters that Mark wrote to Jan and Jan to Mark, and that's how he advanced in his PhD work And I think that he enjoyed Mexico so much. Well, everybody knows he likes Mexico. So he decided to come back, and very soon he came back, and he did in this year. And this was the first of many visits he made to Mexico. We were then, he came later, he made a first course in levy processes, even before the book was written. And he came later, and in 1998 took place the first School of Probability and Stochastic Processes, and we had courses by Blatt Valley and Jean Bertoine. This took place at CIMAT, and this was the first of many schools that we later developed. In this school were already, as students going to the school, Victor Rivero and Juan Carlos Pardo. And so we saw how this influenced the young people. And so we decided to continue this work. And we have, up to now, we have been doing so every 2 years, except when we had other activities. And in this summer school, so Jean always played a very prominent role. He always taught one of the courses, at least for the first 6 schools. And then he began giving talks only, so that other participants could give the courses. And even last year, we wanted to make the 10th school in his honor, but of course, the pandemic didn't allow us to do it. We are planning, if he can still come, to do it next year, so we can still have a 10th school, and we hope we can do so. Not, as everyone here knows, not only he came, but he always encouraged his former students, his friends, his colleagues to come. It's very nice to go to Mexico. It's a very nice country. And it really used to be a very nice country, and it still is, but of course we have many, many problems now, but anyhow. So we can see some of the people who have come. Maybe I forget some other ones, but they are the ones who have participated in schools. And you can see how many of you, which are here, have been there. And we have some of the students who have been in Paris 6 at the beginning, and then at Zurich. So Jan has not broken this contact. He always wants to come back, and he wants to receive Mexican students for continuation, for keeping, as they said, he keeps a sort of a link with Mexico, which is very strong and which we very much appreciate. So we now have a very large community of probabilists in Mexico, and this is in a very large part thanks to the work that Bertoine has done, him and his friends. In the year 2011, Jean Bertoine was elected a member, correspondent member of the Mexican Academy of Science. You can see here in the ceremony where he receives his papers of being a member. And in 2008 took place the France-Mexico Symposium. And I don't think he was there, but anyhow, here we have some of these symposiums here. And there was always a very important French participation, which has given, has developed in such a way that we now have at the Institute of Mathematics of the UNAM, a laboratory, CNRS laboratory, so people can come and spend some time there. And I think a very important part of this being done is the part of the probabilist community who has been going so often to Mexico, and Mexicans coming to France. And so really it's very important, because this laboratory, it's a huge achievement to have this now in Mexico. So this is the second school over there, and this is one of the schools that took place. And we had in the year 2011 also the stochastic process and its application big conference. And also this was a very important event for Mexico to have. And the last school was in 2018. As I said, we wanted one other school in 2020, but this was not possible because of the pandemic. And you can see Loic, you can see Vincent. There is always a very important participation of the French community, and we really appreciate this very strong relationship. So up to now, that's what I'm going to say about this interaction between Jan and the Mexican community. And we really want to thank him very much for all the interest he has always shown in developing Mexican probability. It's really very important. And well, we thank him for all of this. So now I'll start with the mathematical talk. Thank you very much. I did it very. Now I'm going to speak about what we have been doing lately with some of the young mathematicians in Mexico, probabilist Jose Luis Perez, who spent some time in Paris 6, and Adrian Gonzalez Casanova, who hasn't been in France. He mainly did his PhD work in Germany. And well, we have been working during the pandemic, and we have been doing very nice. Well, we think they are very nice. And so the idea of the talk is consists of having what's the motivation for our work, what's our model. We work with two independent continuous branching processes with immigration, the total population, and the frequency of the process. Then we have to go to a martingale problem, and from this martingale problem, we find a stochastic differential equation. These stochastic differential equations will give us an idea of what the lambda frequency process should be, and we can compute the infinitesimal generator. We will see that this stochastic differential equation has a strong solution, and we'll see what the infinitesimal generator is. But we still cannot say what the frequency of one of the types is. Then we have to use the cooling procedure, which is an idea that comes from Gillespie from the 17th. And then we after the cooling procedure, we can be sure that our candidate for the lambda asymmetric frequency process is the good one. I mean, the good one, that means we had the stochastic differential equation, and we now see that by the cooling procedure, it's the really good model for the lambda asymmetric frequency process. Then we study the properties of this process as its limit behavior when the total population goes to infinity and its fluctuation. Then we study duality and coalescence. And then finally, we study an homeomorphism between continuous branching processes and coalescence. The motivation is to describe the interaction between two populations. We have different mechanism. They have, each CBE has a different law. So how do they interact? And that's why we call it asymmetric, because of the different laws of each of the process. So that gives rise to a great deal of models, because we don't need them to have the same law. Some papers since the 17th have studied the problem of two populations competing between them. And I mentioned, as I said, many of you have been in Mexico. Once there was a Mari who teach a course in Guanajuato, who was of population, and many models he explained there. And at the same time, more or less, he published a paper where he gives a nice introduction to the subject. He does many other things, but in this introduction, he explains that when the total size is constant at the beginning, which is an usual hypothesis in population models, then, and they are described by this diffusion, it is well known that the proportion of one type is a Markov process with generator, which is marked there. So we have this model that he explained there, and he also mentions a moment duality between Wright-Fisher diffusion, a solution of this stochastic differential equation, and the block counting process of the Kingman coalescence. And the duality means that, how do I signal? The duality means that if we start the process y at point little y, then to the power n, and we calculate the expectation, this is the same as the expectation starting at point n of this block counting process, y to the power this block counting process. So what we do in our work is mainly have a generalization of these ideas, and I think, well, new things come out of this. There are other papers which establish a relationship between CB processes and coalescence. We have the work of Ekelrich and March on one side, Perkins on the other. They work with time change. And then we have the work of Bertoine and Legal, who observed the relationship between coalescence and CB process. This was done in a series of 3 very nice papers. In the year 2000, they proved that the Bolthausen-Schmidtmann coalescence describes the genealogy associated to the Neveu CB process. And this was done not by time change, not by duality, but introducing the flow, a flow of bridges, which they developed in the second and in the third paper. They are very nice papers. Then we have the work by Berestiki and Limi, who constructed a look-down coupling between coalescence and CB process, and the recent work by Lambert and Johnston, who studied the genealogy of a general CB process, but they only discovered that the genealogy is not a Markovian object in general. It can be coupled with lambda coalescence in small time. Maybe he can tell us more about this, but this is more or less the ideas of the preceding works. So what we do is to work with 2 independent continuous state branching processes with immigration. They are characterized by a branching mechanism phi and an immigration mechanism psi. They have this sort of, not sort of, but a Levy-Kinchin development. And so they can be characterized by the triplet BCM and the mechanism of ramification. Oh, here. We have this triplet that characterizes this formula and the migration. So here we have a Levy-Kinchin formula for a positive, spectrally positive Levy process, and we have a subordinator. So with the usual characteristics, okay? Agua. The other characterization of CBI processes is by a stochastic differential equation that we have also the parameters CBI here, here, and we have two Poisson random measures. We have a Brownian motion, and here we have the independent subordinator, which comes from, which we only leave it like here, like this here. And we can see what the characteristics are. BI is a standard Brownian motion, and they are random, Poisson random measure with intensity measure, each one associated to the measure, the Levy measure, MI, the S, the MI, the U, and the other ones are Lebesgue measures. And we also have the compensated associated random measure and the independent subordinator. They are all independent among them with Laplace exponent phi I. So this is our model. And of course, we have to consider the same quantities. The total mass designed by Z and the proportion of one of the types, which we write Xn divided by the total population. But here we don't want to establish the hypothesis of a total mass constant, because in this model, this wouldn't be very reasonable to do, because the jumps would not enter in this idea of having a constant population. They might go out because of the jumps, of the large jumps. So we cannot have this hypothesis. And we have to, in this case, we don't have that R should be Markovian. So how can we study this process, which is not Markovian in principle? So that's when we read the papers from Gillespie, which are also given in, they are known, and in the papers of Amari, he mentions the work of Gillespie, but maybe he's not very well known. And he worked in the model of having a competition between two types of populations using different mechanisms to develop, but only in the case of two-Feller diffusion. In a first paper, he only does it for the discrete case, and then he does it for the diffusion case. And what he does, the competition is then introduced by sequential sampling. And that's what we will do. We will do sequential sampling, and we will try to find these ideas. At each sampling, the total population, some sampling times, the total population is forced to come back to the initial position. So this is very interesting, and it's also interesting from the experimental point of view, because that's what's done for many experiments, like the Lenski experiment Adrian studied in some of his work. And so this is a nice idea. And he also mentions in his work a new idea at the time, that the role of the variance was very important for the reproduction mechanism. And he found out that decreasing the variance had a consequence of increasing the probability of success. His ideas of sampling is called by us the cooling procedure. So here we see the paper where he established that if some kind of birds would have M eggs, should they put them in one basket or should they try to be evenly distributed into K baskets? He found, well, it's easy to compute the variance in each of the cases, and he sees that the variance in the second case, put them in K baskets, is smaller, and so it would be a better strategy to do so. So, but for our work in our model, we first need a good candidate for the lambda frequency process. So we first prove a martingale property for the bivariate process, and then by assuming zeta constant at sampling times. Now here we sort of assume zeta constant, but in a very special way that leads us to guess what the form of a stochastic differential equation should be, and so whose solution should be the good candidate. But we are not sure it's a good candidate because we just guessed that this should be the answer to the problem. And then afterwards, by the cooling procedure, we will prove that it's really the good candidate. So it's not difficult to see that what we have to do is to apply the Mayer-Ito formula to the function, to this function, and to the semi-martingale. And this leads us to the proposition that this is a martingale. MT equals to f of r z minus f of small r z minus this integral, where this is a sort of a generator, but not exactly a generator, but because we have this stopping times, which play, we have to stop the process here. So we keep the process with some barriers. This is not difficult to prove, but it's very technical. And then we get this result. And inspired in this result, we get a generator for R. Okay, so we have to compare with the original generator, and we see how here, of course, the variance is taking place in several parts, here and here, and we have these parts, these parts which are related to the Poisson random measures, and these parts which are related to the partials with respect to Z, which will not be important in our model. But here we have that it is this operator has this form. Okay, so we have this form of the operator, and we can see that we are agreed with the former things. Here we give all the definitions for each of the factors. We have these factors related to the Poisson random measures, and we have here the value of these factors. So this was one part of the calculation, but this allows us to give an idea of what the stochastic differential equation should be. From this form of the generator, we arrive to this stochastic differential equation, and I say we are not sure it's the lambda frequency process. So that's why I put here first definition of the lambda frequency process. So this equation seems not very nice, but in reality, it is very interesting and very nice, because we can see here, this is the selection factor. This is the mutation, linear mutation factor. It will be seen. This is the continuous martingale part, which will be transformed into a generalized Wright-Fisher process. And these are the coalescence, they will be terms of coalescence and terms of mutations. So this equation, even if it's not very nice to see, it's very interesting, and we shall prove that it's the good idea. So here are the conditions for this formula. We have a Brownian motion, Poisson random measure with intensity the same as before, and we have the compensated measure, and it's in the formula, not here. Oh, here we have a compensated measure and the measure, normal measure, and then we have the measures for the measures here for the immigration. So we have these conditions, and these are the functions that appear in this equation. Okay, so this is equation that will play a very important role in the rest of the talk. And what we can prove is that there is a unique strong solution to the former stochastic differential equation, that the solution stays in the interval 0, 1, and it has a nice property like this one of being bounded by the initial condition R when we have the same set, and it's a failure process whose generator can be given explicitly. The form of the generator will be very important to be able to prove the approximation and for the duality, for computing the duality. So to get the infinitesimal generator, we have to introduce an important transformation in the space of measures of 0 infinity to the space of measures of in 0, 1. So this transformation is defined as follows. We give this transformation of a Borel set is the same as the inverse image of this transformation of the set A, and we compute the measure nu of this set. This is also a transformation that has been used by Amari and Johnston in their paper, or a very similar one. I don't know if it's exactly the same, but it's this transformation which will help us to write the generator. So here is the generator for the process R, the solution of this stochastic differential equation. So we have to prove that this is really the generator, and it's a technical proof. We won't do it here, but we still can recognize the factors which are here as selection and mutation, and we still recognize those factors, but they are written in terms of this transformation. So this infinitesimal generator will prove very important. Now, we make a stop to realize what we have done up to now. We have obtained a two-dimensional Markov process that describes the dynamics of the two populations. Then we have the first component of this process describes the frequency of a specific type of the population. Next, we obtain a sort of generator for the two-dimensional process. Then we propose a candidate for the lambda frequency process. Now we go to the cooling method that will convince us that we have the good candidate. So what's the cooling procedure? We consider a fixed total mass at level Z at time t0. This is at the beginning. And we consider a sequence of homogeneous Markov-Jump processes defined in the following way. We denote the law of this process by PR when it starts at the position R from 0, 1. For each fixed n, the process has jump times given by independent exponential variables with rate n, and the transition kernel is given by this because we know exactly what the joint law of this process is, because it's, well, we have all the properties of this homogeneous Markov process. So this gives us the transition rates. And when we have this situation, what the idea is to have the first component behave as normally and to have the restrictions in A and to leave free set n. But at each sampling time, we make the process, here is the generator of the process with this K, and we think of Rn as sampling the first coordinate at the position at time t1 over n. And then we let the process run for a certain time, and then we force back the process at that certain time, sampling time, to be back at the initial position set. So we can see what happens at each interval. We have this interval, and we start at this time at the initial position set, and we let the process run some time, and then we return to set. And since the times between jumps converge to 0, this should be we should have a sequence of processes that converge. And what do they converge to? Of course, to what we had as a proposed candidate R. So this is the next result, that the sequence of Markov jump process converge to this process as given as the unique solution of the stochastic differential equation we proposed at the beginning. So this is the result. For any fixed set, we have that the process R bar, the sequence of processes we constructed with the sampling method converge weakly in the space of Skorohod. And the proof involves the generators of both processes, because they are failure processes. We take values in a compact interval. And so all we have to do is to prove this convergence strongly as n goes to infinity. But of course, it's again a very technical proof, which I shall not give. But the idea is to work with generators. So everything should work. And now we really have a good candidate, a good, not a candidate, but a really good lambda frequency process. Now we are happy with this, what we constructed. We are convinced that it's okay, because in the cooling procedure, we have the correct convergence. So everything goes nicely. So once we have this process, we begin studying the different quantities and properties of this process. And one of the properties is that for a large population, it converges to a deterministic object. Here it is. And it converges in a very nice way. And we do some calculations for fluctuations around this value, and we can obtain different results for this process. When the population is big, we can do many things, but I do not have much time to go through those. But if you are interested, I will try to do so. So we go to the part of coalescence. Okay, so we recall, everyone here in this auditorium knows what they are. A finite measure in 0, 1 gives rise to the block counting process of a lambda coalescence, which is an n-value decreasing process that has this rate of change. Okay, goes from the state n to the state n minus I plus 1 at this rate with this measure. And this process have a biological interpretation. So they are called frequency process because they arise a scaling limit of the frequency of individuals of a certain time in a generalized Wright-Fisher model. And we have, in light of these facts, we will try to find what the duality is between our frequency process and some coalescent process, generalized coalescent process. We have again the duality I already explained here. So we will show the relationship between lambda asymmetric process, between the one we have now, and a class of what we call branching coalescent process. This class consists of continuous Markov chains, taking values in n with a symmetry point, and we have to introduce these quantities, lambda. Again, we have this transformation, which is very important for defining this lambda ik nu and mu ik l. We have all these quantities here. So the transformation, we recall the equation that defines our process, and we see what the duality is. Here, we have the following real numbers, which will play the role of, which will define our dual. First, we have here a death rate. Here we have a selection rate. Here we will have a branching term, and the branching term depending on the frequency. Here we have a mutation term, which includes the usual mutation plus the pairwise mutation, the coordinate mutation. And here we have the coalescent term, and this is a killing rate. And so what are these quantities? Because here we have now mu bar, lambda bar, and we have to see what they mean. And this is the dual of our process given by this transition kernel. Here we define what these lambda bar are. It's again in terms of our transformation and lambda. Here we have mu bar. And here we have the selection term, which includes this part and all these parts. And we have the kappa term, which was, what was kappa? The branching term here. So we have the definition for each of these quantities, and so we have this duality established. Now you have the definition for each term. So now finally, I shall speak of, well, of a special case when we have the X1 and X2 CB processes without immigration and equally distributed. We have only a triplet, and we have the immigration, which is 0. By our theorem of the generator now of F has only this form. It's much more simpler to see. And this means that R set D corresponds to the classic lambda frequency process, whose dual is the block counting process of a lambda coalescent. So this is much more simpler, and we can use the duality results to see that the moment dual has generator with Q with this QIG said defined in this way. And so this is really the block counting process of a lambda coalescent. And this allows us to, we have here again the definition. No, I went back, sorry. When I went forward. So this allows us to establish a theorem of an homomorphism, which says the following. When we have, we can define, no, I'm so sorry. We consider the metric space L of all lambda coalescents with no atom at one, equipped with the proper of distance over the space of probability measures defined in the space dr plus PD, and then we consider the space of CB processes with a constant B equals to R, which I will show you in the next slide. B should be this quantity. This must be constant. So really, we have an equivalence class of CB processes with this B constant. And we equip them with the proper of distance in the space of probability measures, defined on the space 0T R with the uniform Skorohod topology. Then we have that L and phi are homeomorphics. Phi R. And the mapping that makes the homeomorphism has this characteristic. Every CB process with triplet B, C, nu is mapped to the lambda coalescence associated with the associated measure, which is given this way. And we have an inverse. H inverse is sending a lambda coalescent to a CB process with characteristic triplet. Here is R minus this, which is only the original B, which must be constant. And then we have here set times the measure of 0. And here we have the measure, the Levy measure for the CB process. So this is an homeomorphism. And this is one of the very nice results that come only through the fact that we can go through the cooling procedure to construct the lambda frequency process. So if we didn't have this, this method, we couldn't prove these results. And then we are developing different ways to continue this work. We are now almost done with the bivariate CB process. So we have two processes, X1, X2, but they are bivariate, two-dimensional. So this is like to speak, if we had two islands, each one of them can have two types of descendants. Like if they put them in one island or the other one. And then this gives rise to many interesting examples, since they can have any law. And then we have already arrived to the stochastic differential equation, and we have already found the duality. You can see it in this picture. It's just very schematically written. This is the case for the seed bank model, and we have each term of the stochastic differential equation here becomes something in the dual. Here we have either branching, either coalescence. We have all these situations, and this is almost finished, this paper, and we are trying to work different other models with a random environment and different situations that will allow us to give many models close to the biological models and try to see that they really represent realistic things in biology. So I thank you very much for your attention and congratulations to Jean-Bertrand. Thank you.
Thank you very much, Maria Emilia, for a very clear and interesting talk. We have plenty of time for questions. I guess Jean has a question.
So thank you, Maria Emilia. It was very nice. So you assume that your two continuous state branching processes with immigrations are independent. Is that necessary? I mean, could your method be extended to say two types branching processes? Maybe there are some elements of the answer which you already pointed at the very end of your talk. Two types. I mean, instead of having two independent branching processes, you have a single one, but with two types, and you consider
we haven't done that. We have two independent continuous state branching processes, and in dimension 2. So each individual gives rise to two types of individuals. So we have in the whole thing, they can have here individuals or here, no, here. And they can jump from one island to the other. So this should be different individuals. What should I put? Different color and a different color. This is not only one single CBI process having two types of sons. No, we have two populations competing, but they have two types of sons, maybe like active or dormant. We could say they have active sons or dormant sons. And also these different type, they have active or dormant, and they compete between them. They can go from one side to the other. But we have two populations, always two populations. We haven't thought of the model of only one population. We haven't thought of that. Having one population, having two types of sun competing between them. But that would be very interesting, of course.
I also want to mention that people in the chat can unmute themselves if they have questions. Other questions? I have one.
Okay.
So you use this curling procedure to basically condition the process to be constant, right? The Z process to be constant. So each time you resurrect the process at its initial state Z, you keep the same value for R, right?
Yes.
Yes.
R continues to behave like it should, but we force Z to go back to the initial value at each sampling time.
Could you do the same thing but upside down, like conversely, have R come back to its initial state and Z and let Z evolve, so that instead of having a law for the frequency process condition on the total population size to be constant, the contrary, having trying to get information on the total population size when you actually only have information on the frequency process?
Yes, I suppose it could be done. I mean, fixing the first component as a constant, bringing it back, force it back to a value. Yes, I suppose it could be done, of course.
I also wanted to ask you, so in the when you look at the lambda frequency process, you have this killing rate, Does it correspond to like finding immigration events in the forward process?
Yes.
Yes. Okay, so you're able to you're able to actually have a generalization actually of the lambda coalescent, since you have now lambda coalescent with death.
Yes.
Yes.
Exactly.
Okay. And the relation that you get between the homeomorphism that you described is not bijective, right? Between the lambda coalescent and the CBI or CB processes, it's not bijective.
It's what? That I didn't get.
So when you describe the map that takes you from the CB processes to the or let's say the CB process characteristics to the lambda coalescence, we see that you lose some information on the growth rate of the process, right? Because you have to consider that R minus that B is constant.
Yes.
Could you comment on that? The fact that it seems
What's that? The meaning of that condition?
Yes.
No, we haven't thought of that.
It seems that actually, if when you look at the coalescent of a CB process, the fact that it might grow or increase or decrease through time will not affect the coalescent, and so you lose that information in the coalescent. You lose information on the increase or decrease of the population size.
Yes.
Yes. Okay. Thank you very much.